So I think we all know what AWS S3 is, right? The super popular multi-tenant storage service used to store most of our data objects. But did you know that S3 still to this day uses hard drives instead of SSDs? And did you know that this architectural decision has enabled them to scale up to speeds of 1 petabyte per second? How is that even possible? Well, that's what we're gonna find out in today's video. It's gonna be a lot of fun, so let's dive into it. I recently stumbled upon this amazing article by Stanislav Kozlovsky where he dove in full detail on how S3 managed to become the behemoth they are today by using something as archaic as hard disk drives. So first of all, let's take a second to appreciate how powerful S3 actually is. They've been able to store more than 400 trillion objects. They can handle 150 million requests per second. They have speeds of more than 1 petabyte per second. And they can achieve all of this because they have tens of millions of hard drives at their disposal. I'm sure we're all asking the same question. Why hard disk drives? They're such an old piece of tech with constrained input-output operations per second, or IOPS, and they have a high latency. Well, it turns out at its core, the simplest reason is money. Check out this graph. Over the years, memory costs have gone down significantly across the board. But even with all of this, disks are still twice cheaper than solid drives. And when you're AWS and you're buying millions of them, every dollar counts. Okay, so they're cheap, cool, but that doesn't solve the performance issue. In fact, for the past 30 years, hard drives have been stuck at 120 IOPS and haven't evolved much. Now, why is that? Well, that just comes down to simply real-world physics. You see, SSDs use electricity, which is traveling at roughly 50% of speed of light, while hard drives are using mechanical actuators that move read-write heads across multiple spinning disks. And that means accessing data involves 2 mechanical operations and 1 electrical operation. First, the actuator seeks the correct track on the disk platter, which can take up to 25 milliseconds to finish. Then, the spindle rotates the disk until it matches the precise address on the disk, and that can take up to 8.3 milliseconds. And then the data is transferred to memory, and for a half a megabyte, this can last about 2.5 milliseconds on average. And due to this nature of transferring data, hard drives are optimized for sequential access patterns. This means that reading and writing bytes that are laid out consecutively on disk is pretty fast. And if this is the case, then the natural rotation of the platter disks allows for sequential reads and writes, and in the best case scenario, the actuator just stays still. It doesn't have to do anything because all the data is just coming in sequentially. This access pattern is called the log, and it's also what Apache Kafka is built on. So essentially, writes are pretty easy for S3 to handle. They just do them sequentially and take advantage of the hard drive's performance. Reading, though, is a lot trickier. Think about it. If you don't really know where exactly on the disk the correct address you're trying to retrieve is, then on average, it would take half a rotation to get to it. Therefore, the average read latency is the sum of both average physical movements plus the transfer rate. And for half a megabyte, that is roughly 16 milliseconds, and that is very slow. So with all of this, you're looking at 32 megabytes per second reading speed on average, and this is exactly the performance bottleneck that hasn't evolved much for hard drives for the past 30 years. But even with all these limitations, AWS has still figured out a way to achieve low latency and outstanding throughput. And here's how they did it. First of all, they are performing massive parallelism. Think about it. If you wanted to store a 1 terabyte large file on a single hard drive, you would be limited by that drive's maximum throughput. But if you spread the file across 20,000 different hard drives, you can read it in parallel at the sum of all the hard drive's throughput speeds combined. But technically speaking, how does S3 actually do that? They do it with something called erasure coding. Erasure coding means you break data into K amount of shards with M amount of redundant parity shards. Erasure coding allows you to reconstruct the data from K shards out of the total shard count. There are many ways you can configure erasure coding, but S3 uses a combination of 5 regular shards and 4 parity shards. This way, they are able to distribute load evenly and also steer the traffic in a balanced way. Okay, so this is all cool. With these techniques, they've now managed to achieve 1 petabyte per second speeds with hundreds of millions of parallel requests per second and hundreds of millions of drives working simultaneously. But they still have one more problem to solve: the hot partition problem. How do you avoid hotspots? How do you spread the load evenly across millions of drives to avoid certain disks from overheating? After all, as we figured out earlier, a single disk peaks at around 32 megabytes per second on reads, and it seems almost certain that they would hit that bottleneck at some point. And this is also dangerous for a large system because as soon as one disk hits that peak, it can quickly cascade to other disks and degrade the whole system. Well, AWS have managed to solve this hot partition problem in 3 different ways. First, they randomize where you initially place the data. Ideally, you would want to place your data shard in the least loaded hard drive, but unfortunately, there is no easy, efficient way to find this drive across millions of drives. So the solution is actually ridiculously simple. It's called the power of 2 random choices. It's a well-studied phenomenon in load balancing, which states that choosing between the least loaded of 2 completely random nodes yields much better results than choosing one random node. So basically, they just pick 2 random disks, choose the one that has more space, and puts it there. This is fast, and weirdly enough, it just works. The second way AWS solves the hot partition problem is by rebalancing. Here's a key observation. Newer data chunks are almost always hotter than old ones. And just by knowing this, we can predict that fresh data will be accessed more frequently. So AWS proactively rebalances old data as part of their routine to avoid this issue. Plus, if they install a new server rack, it's completely empty, so they need to rebalance that as well to spread the load. And finally, the third way AWS solves the hot partition problem is with workload decorrelation. So one of the many reasons why hot partitions might happen is here. Because if we look at a single individual workload, it can be very bursty. There might be times where requests really spike up. And ideally, S3 wants to avoid these sudden bursts at all costs. But here's another interesting key observation. The larger a system becomes, the more predictable it gets. And this is a phenomenon AWS witnessed as they grew. Since all independent workloads don't burst at the same time, the more workloads you have in the system, the more idle spots of your system gets filled up, and the more the system stabilizes in aggregate. So in other words, it only works if you're a billion-dollar behemoth company. So that's basically it. That is the surprising reason why S3 continues to use hard drives instead of SSDs. And it seems to be working great for them. This was also so mind-blowing to me when I first read Stanislav's article, so if you want to dig deeper into this topic, go read his full article, and I will also link it in the description below. And thank you folks for watching. If you like these types of technical breakdowns, give this video a like, and don't forget to subscribe to our channel. This has been Andres from BetterStack, and I will see you in the next videos.